Okay, welcome everyone. So it's a pleasure to have with us today from Cambridge, Tom Hutchcroft, and slides are shared, so we can get started.
Thanks. It's nice to be back, if only virtually. Thanks for the invitation. So I'm going to be talking about long-range percolation. So let me just start by saying what that is. So long-range percolation is very similar to Bernoulli percolation. It's just that instead of starting with a graph and then deleting edges, we sort of imagine we start with no edges and then we're sort of randomly adding edges. But of course, this is equivalent, but it's just nicer to think of it this way. So in particular, I'm going to be talking about long-range percolation on ZD. So we start with all the points of ZD and no edges. And we have some function J, which is going to describe the probability of putting an edge between 0 and x. So the only things we're going to assume about this function J is that it's integrable, which just means that basically it's going to mean that when I do my long-range percolation, the graph that I get has finite degrees. Obviously, you can study the other case as well, but it's not the questions that you would look at are different in that regime. Okay, so I'm going to be looking at the integrable regime, and I'm going to assume that it's symmetric, which just means that j of x and j of negative x are the same. So what we do is we take this function j, which is this kind of intensity function, which is describing the manner in which our model is long-ranged. We also take another parameter beta, and we say that we include each possible edge, xy, is actually made an edge independently at random with this probability 1 minus e to the minus beta j of y minus x. Okay, and this specific choice of function is not really important. The point is that when y minus x is large, this is basically beta times j of y minus x, and it's always between 0 and 1, so this makes sense. I mean, this is really the only reason we use this function. You could just take the max, the minimum of this, and 1 would work. Everything would be exactly the same. Okay. So in particular, any pair could be an edge, and there's no special role for nearest neighbors. So although you could take j to be the indicative function that x is a neighbor at the origin, and then this model becomes equivalent to nearest neighbor percolation. Okay. But we're going to be interested in the case that j decays like a power law. So in particular, we'll be interested in the case that j is roughly like the distance to the minus b minus alpha, where alpha is some number strictly larger than 0. Okay, and I'm leaving this vague for now. In fact, all our results will be true provided you just have a lower bound of constant times this. Okay. And why do we write it this way? Well, if we took a power of x that was decaying more slowly than this, then we wouldn't be in this integrable regime. So if we're interested in the integrable case where we get like finite degrees in our percolation model, we need to have a power bigger than d, so it makes sense to write it this way. Now, as in normal nearest neighbor percolation, we expect to have a phase transition. So there should be some special value beta c, where below beta c there are 0 infinite clusters almost surely, and below beta c there's a unique infinite cluster almost surely. Now, of course, we don't necessarily have a phase transition, particularly in one-dimensional models. So what happens is that in one dimension, there's a phase transition if and only if this parameter alpha is smaller than 1, whereas in higher dimensions, just the standard arguments give that there's a phase transition for any value of alpha. Okay? And you could imagine what happens if you did set alpha to be equal to 0 or negative. What it would mean is that beta c would be equal to 0. So these questions of phase transitions are not interesting in that context. So you should think of the smaller alpha is, the more long range the model is. Bigger alpha makes it harder to have long edges. Now you might think that this model ought to be maybe more difficult than nearest neighbor percolation, but in fact that's not really true. So in fact, our understanding of long range percolation is better than our understanding of nearest neighbor percolation in several ways. So in particular, at least for small values of alpha, the continuity of the phase transition is completely understood. And of course, this is not the case whatsoever for nearest neighbor population. So in particular, if you look at the case where alpha is strictly smaller than d, it's a theorem of Nürnberger that the phase transition is continuous when alpha is strictly smaller than d. So in other words, if you look exactly at the phase transition at B to C, where you go from having no infinite clusters to at least one infinite cluster, you in fact have 0 infinite clusters at B to C. Okay. And this condition is actually necessary, at least in dimension 1, because it's also a theorem of Eisenman and Newman, that if you're at d equals 1, alpha equals 1, then you actually get a discontinuous phase transition. This is something very important to know if you're interested in, for example, proving that there's no percolation at criticality for nearest neighbor percolation on Z3, for example, because you find actually many arguments that work for nearest neighbor percolation also work for long-range percolation. And so this is something worth bearing in mind if you want to prove that. Any proof strategy that you have for proving that there's no percolation at criticality better not apply to this example. Just to give you some intuition of why this alpha strictly smaller than d equal to d bigger than d thing could be important. If you look at, suppose you take two boxes that are of side length n and they're separated by a distance of order n. Okay? Then you can compute how many edges do you have going, just one long edge going from one box to the other. Okay, well, you can, there are n to the d squared possible endpoints, and each edge is present with probability n to the minus d minus alpha, so you get this, in expectation at least, n to the d minus alpha edges. So that means when alpha is strictly smaller than d, the boxes separated by a macroscopic distance will in fact have a large number of edges going between them. When alpha is exactly equal to d, it's order 1. And then when alpha is larger than d, you typically don't have any. So geometrically, this is giving an indication of why there's something going on at this alpha equals d. Okay. And in fact, in Berger's proof of this theorem, it's very clear how this is used. So I'm going to be talking about the new proof of the theorem, which is actually less clear how this thing enters, but it must do so. Now, the way that Nürnberger's proof works is what he really shows is he says, suppose you have some value of beta where you have percolation. So he shows that for any such value of beta, you can in fact decrease beta a bit and you'll still have percolation. In other words, he shows that this set of beta where an infinite cluster exists is open. So proving continuity this way it's nice and it's often how we do it, but it doesn't really tell you anything quantitative about critical percolation, typically. So what I want to tell you about today is a new proof, the same theorem, but which follows a completely new strategy, and it gives much more quantitative information. So we're going to have the same assumption, and you might complain that I didn't really define this properly earlier. So here's the concrete thing: is I'm just going to assume that I have a lower bound of this form. So j of x is at least a constant times mod of x to the minus d minus alpha for sufficiently large x. Then, given this assumption, theorem is that there exists constants, so that the probability of, so this is my notation, KV is the cluster of V, in other words, the connected component containing V in this random graph. And so the conclusion is that the probability that the cluster at the origin is large satisfies this power law upper bound. Probability that it's larger than n is at most constant times minus the minus alpha over 2d plus alpha. And also we get a bound on what's called the 2-point function. In other words, the probability that 0 is connected to x. And again, we get a power law bound here, except the proof doesn't give a pointwise bound. It only gives something about the average x. So if you take a typical x in the ball of radius r, then you get this bound. The most interesting case of this theorem is when d is not too large and alpha is not too small. So if d is bigger than 6 or alpha is smaller than d over 3, then we expect percolation to have what's called mean field behavior, which basically means that the cluster at the origin kind of behaves like a branching process. In particular, in this mean field case, you'd expect to just have a half here. So the probability of the volume being bigger than n should be like 1 over root n. And this, you'd also expect that this 2-point function should behave like the Green's function. Of course, for long-range models, it wouldn't be the Green's function of simple random walk, it would be for some appropriate heavy tail. Yeah, but these things are expected to hold either when the dimension is bigger than 6 or when alpha is smaller than d over 3. And in fact, we know for many classes of examples that this really does hold. So this follows from a work of Hara and Slade in the early 90s for the nearest neighbor models and also for long range, but with fast decay. And these power law decay models in the work of Chen and Sakai. So I have this written down later on. So references. Okay. So, but this is really interesting when we're not in this mean field case. So that we don't know. Well, we have an idea of what the correct exponents should be, but we really don't know how to prove them, except in very special cases like planar lattices, where there's necessary technology and so on. Okay. And just to mention, for those who are interested, nothing I'm going to be talking about today is really very specific to ZD, and you can formulate a version of this theorem for sort of arbitrary groups, and it's all. Okay. So let me now interpret this result in terms of critical exponents. Okay, so of course, most of us know that when you have these kind of critical statistical mechanics models, you expect them to be described by some sort of critical exponents. So two particular ones that we might look at here would say, so for percolation, there's delta and eta, among many others. So delta describes the distribution of the volume of the origin, the cluster of the origin at criticality. So it's supposed to be like this power law. And you know, these notations are traditional, but they're a bit strange sometimes. Delta should not be thought of as a small number. It's always bigger than 2, in fact. And then the 2-point function exponent is normally expressed this way. So it's like the correction to Green's function scalar. So if eta is 0, you have the 2-point function is like the Green's function, and otherwise it's different. Okay. So under these mean field conditions, we expect or know in many cases that that these exponents are well defined, and delta is equal to 2 and eta is equal to 0, right? Which I. Okay. In fact, we always have that the probability of criticality of having size at least n, it's always lower bounded by a constant over root n on any transitive graph or long-range model or whatever, by result of Eisman and Barsky. So in fact, delta is always at least 2 if it's well defined. Now, if you take this theorem that I wrote above and you just see what it means in terms of these critical exponents. It means that if they're well defined, they satisfy these two inequalities. Okay. So maybe you don't know what to think of this yet. So let's see how this compares with what the physicists believe about the true values of these exponents. And actually, I didn't really know what the conjectures were about this until I was working on this paper, and it's really nice and surprisingly simple what the conjectures are. I should say this is really, I should have written it down, but these projections come from the work of Sachs in like the 70s, 80s in the physics literature. So he was thinking about the Ising model, but the predictions are the same, essentially. So what they say is as follows. So first of all, in one dimension, yeah.
Yeah, sorry. So in your theorem, you get a point bound as well.
Yeah, it's point to point, but it's averaged. Okay. So, but if the exponents exist, then the average and the specific are the same, right? Because that's part of what it means for it to exist. So the prediction says, first of all, in one dimension, 2 minus eta should be equal to alpha. At least, when alpha is less than 1, otherwise there's no phase transition when alpha is bigger than 1. Okay, so the graph just looks like this. And of course, that means that when you're exactly at 1, you get that 2 minus eta is 1, and then you get that there's no decay of the connection probabilities, which is suggesting that the phase transition is discontinuous, which it is by the theorem. Okay, and if you take this prediction, which is incredibly simple prediction, and then you combine that with what are called the scaling and hyperscaling relations, which I'll talk about later, you get this predicted value of delta, but it has the graph has two pieces. So when alpha is less than a third, the model should have mean field behavior. So delta should be equal to 2. And then when alpha is larger than a third, you should get this simple rational function 1 plus alpha, 1 minus alpha. Okay, so this is the prediction for one dimension, and I believe it's open to prove this. I think the lower bound is known from the same work of Eisenman and Newman, where they showed this continuity, I think, although I should have checked that carefully. Anyway, I think the lower bound is known, but the upper bound, I believe, is not known. I think that the results I'm telling you about today are the best, so that they're not sharp, they don't establish this. And then what's supposed to happen when you go to 2 dimensions and higher is that there are kind of 2 phases. So when alpha is small, you should get the same thing. So when alpha is small, you should just get the 2 minus eta is equal to alpha, as in the one-dimensional case. Okay, so this 2-point function is getting worse and worse. It's getting bigger and bigger until you hit the exponent that you should get for the nearest neighbor model, and then it stops changing. So that's the prediction. So you should have these 2 phases, the kind of small alpha phase and the large alpha phase, where in the large alpha phase, it should behave exactly the same as, all the exponents should be the same as the nearest neighbor model. And in the low alpha phase, it should just be the same as the one-dimensional model.
I have a question.
Yes.
Do you mean alpha min 2 minus eta SR?
Yes.
Okay.
Thanks. Yeah, so you kind of have this small alpha phase where the long-range behavior is dominant, and actually the geometry of the lattice is basically irrelevant. I mean, it behaves the same way as like a hierarchical model. And then this is supposed to switch into this large alpha case where the model behaves the same way as the nearest neighbor model. And then you know, if you get really into it, you can look at, well, what happens when you're exactly at this point when the two different behaviors are equally strong somehow, and there's conjectures about what happens there as well, and it's super interesting. It seems probably super hard as well. There are some results, though, in the high-dimensional case by Chen and Sakai recently. So how do the bounds I'm telling you about compare to these conjectures? So I have these two graphs copied from the paper here. So so the blue line is the bound that I prove, and the red line is the conjecture. And you know, they're okay. I think is the answer. They're not wildly wasteful. So in particular, if you're in this regime where you expect to have the long-range dominant behavior, the bounds that I get on delta, for example, are always within a factor of 2 of what's conjectured to be the true value. So of course, we'd really like to do a lot better than this and prove the conjecture, but this is, I think, a nice start, and it's not completely crazy. So let me start telling you about the proof, and I'll start by just zooming out very far. And I apologize, my handwriting looks quite bad on this page, so if there's anything you can't read, I'm going to be saying it all anyway. So roughly speaking, there are 2 high-level strategies that people have approached the problem of continuity of phase transitions for percolation. So the way I like to think about them is in terms of what's what I call the supercritical strategy and the subcritical strategy. Okay. So in the supercritical strategy, what you try and do is similar to what I said about Berger's proof before. So you take some P, which might be PC, but you don't really want to assume that necessarily. And you assume that there is percolation at P, and then you try to deduce that if you decrease P a bit, then there's still percolation. And often the way you do that is you argue, well, if infinite clusters exist, then they have to be sort of big in some sense. So you might want to argue, for example, that they look like the graph that you started with in some sense. You want to prove that in a strong enough sense that, well, I know the graph I started with has a phase transition for percolation. It has PC less than 1. So if I can show that this infinite cluster has PC less than 1, well, then it would follow that if I decrease P a bit, then I still have an infinite cluster. So I've shown that the set of P where infinite clusters exist is open, which is what I want to do. Okay, and you know, there are various ways of formulating essentially this strategy, and it's been pursued very effectively in a lot of works. I'd say most proofs of graphs having continuous phase transitions are of this kind, and this is certainly the most popular approach that I know of to trying to solve the open problems about Z3 and things like that. Now, on the other hand, and Berger's original proof of this long-range theorem certainly falls into this. And on the other hand, there's the subcritical strategy. So here the idea is to show that the set where you do not have infinite clusters is closed. And the way you try to do this is you try to prove that there's some non-trivial upper bound on the distribution of the cluster at the origin that holds uniformly throughout the whole subcritical phase. Right? But if you prove a bound like that, it follows that it holds at PC as well. Right? So for example, you might want to show that there's some bound on the probability that X is connected to Y that decays to 0 as the distance between the points goes to infinity, and that it holds on the whole subcritical phase. Okay. Now, there are a few ways where you can do this, and there are actually some very special cases where you can do it directly. But the more sophisticated versions of this argument typically rely on what's called a bootstrapping argument. So in particular, this really comes from the work of Gord, both on percolation and the earlier work on self-avoiding walk. At least that's the place that I know that introduced this idea. So you want to show basically that some non-trivial bound. So what I mean by non-trivial here is really that this bound would suffice to show that you have no infinite clusters. You want to show that there's some non-trivial bound that implies a strictly stronger version of itself. Okay, so you might think that sounds stupid or circular or something, and well, to an extent it is circular, but it's a circular argument that works, so it's nice in that sense. So the classic example of this is the lace expansion. And this isn't really how the lace expansion for percolation works, although it is basically how the lace expansion for self-avoiding walk works, the weakly self-avoiding walk. So what you want to say, for example, is that suppose I can prove that I'm in high dimensions, and I can prove that if I have a bound of this form, saying that the probability that x is connected to y is always bounded by 3 times the Green's function, then in fact I have the same bound, but where 3 is replaced by 2. Okay? So if I can somehow, it's a big if, and this is all the amazing work of the lace expansion that goes into proving this implication in high dimensions. But if you can prove this, that this bound with a 3 implies a bound with a 2, then in fact you can deduce by continuity that the strong form of the bound with the 2 holds uniformly on the whole subcritical interval. And basically the reason why is, well, you have to be a bit careful because the sort of quantification of infinitely many things and stuff like this, but it's basically a continuity argument. If I ever started to go a bit above this 2, then I'd still be below the 3, and therefore I'd be back below the 2 again. So it's not totally immediate, but this implication plus the continuity argument means that this bound holds whole subcritical interval, and then you're done. You've proven there's no percolation at PC, and in fact you've proven way more because you have this quantitative bound. Okay. So our proof is also going to be based on a bootstrapping argument like this. But unlike in the lace expansion, we're not going to try to prove an optimal bound. The lace expansion is really, it's all about identifying exactly what should be going on and then proving that that's what goes on. We're going to try to do something that's a bit more, we have a bit more room. We're not really going to try to get exactly the right thing. I mean, I tried to optimize it as much as I could, but it's going to work without zeroing in on exactly the right behavior. It's going to build on some ideas that we used to analyze percolation in some other settings, so in particular originally on groups of exponential growth, and then also with Jonathan, we looked at groups of intermediate growth. I actually gave a BBC probability seminar talk about this a year or two ago, maybe. But it's going to use some similar ideas as well as some new ones. And one of the main inputs is what I call the two ghost inequality. So this is something that's based on similar ideas that appear in the paper of Eisenman, Keston, and Newman. Who proved they were the first people to prove that on ZD there's at most one infinite cluster for percolation. So most people now learn the Burton-Keene proof that came a couple of years later, which is simpler and more general. But the Eisenman, Keston, Newman proof is very interesting. It's completely different. And it also tells you more interesting quantitative things. Basically what they show is that if you have a box and you take some edge in the middle of the box, then the probability that you see this event where the edge you look at is closed and its endpoints are in distinct clusters that both go to the boundary of the box is bounded by, their proof gives something like log n over root n times constant. They actually didn't write down this explicit bound, but it follows from their proof. And this kind of went, people, probably partly because it wasn't explicitly written in their paper, it took a long time for people to realize how useful this bound was in this form. Really, Raphael Cerf had a 2013 paper or so that really reignited interest in these methods, and he showed how you can prove this in various ways. So this theorem here is very much along the same lines, except it works with volumes instead of with radii, basically, which makes it better suited to long-range percolation. It's also better suited to graphs other than ZD, and even in ZD, it's just, even in nearest neighbor percolation, it's stronger than this because you use volumes instead of radii. Yeah. And so in our setting of long-range percolation, what it says is that if you sum over all x, and you look at this probability of the event that the origin and x are in distinct clusters that both have size at least n, they both have at least n vertices, and at least one of them is finite, then this is bounded by some universal constant, which is like 50 or something, divided by root n. Okay, except you have to multiply it by this factor to do with the weights, okay, which is roughly square root of beta times j of x. So what it says is that, what it says is that these kind of events where you have two big clusters that are distinct, that are near each other, have low probability in this totally universal way. So depending on how much time we have, I might discuss the proof of this at the end. I think I actually presented it in the previous seminar I gave a while ago, so I'll only talk about it if we have other things to talk about. It's a very nice argument of okay, so what I want to do now is show you how we can use just this bound as I've written it here, and we'll come back to stronger versions of this later on. Let's see how we can use just this bound to prove a weaker version of my theorem, where I'm going to have this stronger requirement on alpha, that it's smaller than d over 4 instead of smaller than d, and the exponent that I get is not as good. Okay. So how are we going to do this? So we want to use a bootstrapping argument. And the specific one we're going to use is, so I'm going to call this value the exponent theta. So what I want to show is the following implication. So I'm going to assume that beta is not too close to 0. So let's just say it's between beta critical and beta critical over 2. This is pretty arbitrary. And what I claim is that there exists a constant, so that if you had an upper bound of this form, where you know that the probability of having a big cluster is smaller than a n to the minus theta for all n, then in fact you have the same bound, but where this constant a has been replaced by some fixed constant times the square root. Okay. So let's see why this, if I can prove that this implication holds for all a, so the claim is that for all a this holds. Let's see how we conclude from here. Well, we just define, for each beta, let's define a beta to be the best constant we can put here so that this inequality is true. Okay. Now we know that by what's called sharpness of the phase transition, that if I'm below beta c, then in fact the volume of the cluster at the origin has an exponential tail. Okay. So in particular, if I'm below B to C, then I must be able to put some constant A here so that this inequality is true. So A beta is less than infinity. Okay. But this implication here says that A beta is smaller than this universal constant C times the square root of A. Right, but A is finite, so I'm allowed to rearrange this and I get that A is bounded by C squared. Therefore, this bound with A equals C squared holds for the whole interval beta C over 2 to beta C, say, and therefore it holds at beta C as well. Okay, just by monotone convergence or whatever. I mean, this function is increasing in beta and continuous for each fixed n. I mean, it's like in nearest neighbor percolation, it's a polynomial.
Why do you care about beta C over 2?
I just need, it's going to be important. I could take this to be epsilon and the constant C would depend on epsilon. It's just how the argument works. You won't really see this in my overview, but small beta is annoying for the argument. It makes the constants blow up. It doesn't matter because you're only interested in beta near beta C. Okay. So let's see how this is going to work. So I want to prove this implication here. Okay. So let's take lambda r to be the box minus r to r to the d. Okay, and let's fix some value of beta. And let's suppose that this inequality holds, right? So we want to deduce that the stronger inequality holds, or at least it's stronger when A is large. Okay. Well, first of all, let's try and get a bound on the 2-point function. And we can do this in an extremely naive way. So we just say, if I sum over all x in the ball of radius r, well, that's equal to the expectation at the intersection of the cluster with the ball. Right, but that's bounded by the expectation of the minimum of the cluster at the origin with the total size of the box. Okay. And I can always write an expectation of this form in this way. Right, and then I just plug in my bound here and I do the computation and I get a bound of this form. Okay, so this assumption here is converted into this 2-point function bound of this form, where C is some constant that depends on theta. Maybe not even. Anyway, constants depending on theta as well. Okay. Now, how are we going to use this 2-point function bound? Well, let's look at this event Fxn. So this is the event that the two-ghost inequality gave us control of. So it's the event that the origin and x are both in clusters of size at least n, and I'm below beta c, so they're definitely finite anyway. Okay. So what does the two-ghost inequality tell us? Well, if we look at it, here it's a sum over all x with this prefactor depending on the j's, and then this probability. Okay, so if I just sum over x in this box, I know I have some lower bound on what these are, at least when x is large, but the small values of x are irrelevant, right? So I can rearrange that into saying that this sum here is bounded by a constant times r to the d plus alpha, which is cancelling this guy, and then the sum of all zd of this thing I had before. Okay, and then I just apply the theorem and I get this bound. Now, on the other hand, we can lower bound the same quantity. If I give you a particular x, I can say, well, I want to look at the probability that I have these two distinct large clusters. Okay, well, that's at least the probability that both clusters are large, minus the probability that they're not distinct, right, by a unit. Okay, but the probability that they're both large, these are two increasing events, and we know that for percolation, increasing events are positively correlated. So the probability they're both large is at least the probability one of them is large squared. Right? By transitivity, they're the same. Okay, so I get this inequality. So if I sum over x in this inequality, I get, and then I move this onto the other side and then average over x, I should say. right, we get that the probability the cluster is large squared is bounded by this sum of the 2-point function, the average, plus the average values of the probabilities of these events, right? And I've already bounded both of these. So I plug in those bounds, I get some expression here. It's not too interesting. And then throughout this whole thing, R was just an additional parameter, right? So we can now optimize over R. Turns out the optimal value is this. And if you compute, what you get is that this is bounded by this. Okay? And of course, this value of theta was chosen so that this would work. And if you go through the computations, you'll see that it does work. Okay? But this is exactly what we wanted, right? I mean, it's not exactly the same form this is form. Okay? Because here we have the square, so we take square roots to set both sides, we get that this probability is at least square root. In fact, A always has to be bigger than 1, so that's fine. Okay.
In the
So
two ghost inequality, do you assume anything about the distance between the origin or x, or it holds for any 2 points?
The two ghost inequality is about a sum. Right, so you sum over all x, but you have this factor that depends on the weight. Right?
Yeah.
So what we did here is we wanted to estimate this sum over x in a box, but what we know is how to bound the sum of all x, but with this factor. But by assumption on J, we know roughly what this factor is, so we can, at least inside the box, so we can pull it out and we get this inequality between them, right? Because we assume that J of x is always at least some constant times x to the minus d minus alpha. Is that clear?
Yeah, I just got confused between earlier versions of this inequality.
Yeah, right. I mean, when you're in the nearest neighbor case, normally the way we wrote it was just in terms of a single x, right? I mean, you just bound a single x by the sum, basically. That's the same. But in the long range case, you really need to think about it in terms of a sum.
I also have a question about the two ghost inequality.
Yes.
So how general do you think this might be pushed? Like, does it work for example, finite graphs? Some version of this?
That aren't transitive, you mean?
Yeah, maybe non-transitive.
So for transitive graphs, everything is fine. I mean, it's just you need modularity, but that's fine in the finite case. But arbitrary finite graphs, I mean, the proof tells you something, but because it's actually this inequality really, there's a version of it that holds for all reversible random rooted graphs actually. And you can do percolation in random environment and stuff like that. It's actually super general. If you're interested in this, my paper on the Ising model.
But how,
well, I didn't write it for reversible random graphs, but it's the same.
Okay. I mean, my question was how crucial was the mass transport, but maybe we can talk later. Yeah.
Oh yeah, the mass transport seems very crucial. There are things you can prove without it, but they're different.
Okay.
Yeah, we'll talk about it later.
Okay.
Okay, so we've now seen, this is a complete proof under these stronger assumptions and with the weaker conclusion. Now, the proof of the full theorem is going to follow exactly the same computation, but it's just going to have 2 improvements made to it. So the first one, which is the one I really want to talk about today, is that you see, we had this argument here where we wanted to use this assumption about the tail of the volume to get this average function bound. And this step here is extremely wasteful. It's just a bit silly. Just bounding this intersection by the minimum. This is not a good bound. So we're going to want to revisit this and try to do something better. Okay, so that's mostly what I want to talk about today. This is going to has some cool new stuff. The other thing is that there's an improved version of the two-ghost inequality that I'm not really going to talk about, but it's written here. So this improved version has two features that make it nice. One is that here I'm taking this bootstrapping hypothesis, I'm including it in the hypothesis of the two ghosts and getting a stronger conclusion where I have a better power of n here. But the other thing, which is actually the more relevant thing that really gives it a lot more juice, is it handles large X much better. So, you know, it's probably not so clear why it's so much better unless you really work with these things and do computations. But, you know, the factor I have here is different, but I've got a square here, and anyway, it just works better when you're doing the computations that we want to do here. So I think I'm not really going to talk about this improvement because the proof is really mostly the same as the existing version of the two-ghost inequality. So what I really want to talk about is this. So how are we going to find a better way to convert these assumed bounds on the tail of the volume into two-point function bounds? So the idea is going to be, this isn't really the idea, it's just a name for what we're doing, is that it's hyperscaling inequalities. Okay, so let me just remind you of some of the background on here. We don't really need to know the background, but it's interesting culturally. So as I said before, we expect our critical percolation models to be described by these various different critical exponents. I've written down a bunch here. There are, well, you know, you can always define more critical exponents, but you basically, when you have something decaying or blowing up as you approach PC, or if you're at PC and you look at the tail of some investment variable, you typically expect all these things to be described by these power laws. Okay, where again, I'm leaving the definition of this intentionally vague. Often it will really be exactly like this in some very strong sense. In other cases, like when you're in six-dimensional percolation, for example, you expect there to be some subpolynomial corrections like powers of log and things like that. Okay. But we have all these exponents, and you know, a big conjecture is that they exist. And a further conjecture is that not only do they exist, but they satisfy various relationships between them. Okay. So in particular, there are what are called the scaling relations. So these are expected to hold for every dimension, and they're also not really anything to do with percolation. You know, these same relations are supposed to hold for basically any reasonable model undergoing a critical, undergoing a continuous space transition. Right. So there are these relationships. So maybe just to explain one, so you can see these aren't so complicated really, they're just quite natural heuristic relationships. So if we look at this last one, so the gamma, so gamma is the exponent describing how the expected size of the cluster blows up as you approach PC from below. So if you're PC minus epsilon, the expected size of the cluster at the origin should be like epsilon to the minus gamma. Okay, and eta is the one we already saw, right? It's the says that the two-point function is like x to the minus d plus 2 minus eta. Okay, and nu is describing the correlation length. So the correlation length, what it means is that it's the length at which you start to see that the model is subcritical. So if you're at PC minus epsilon, if you look at the two-point function between 2 points, it should be roughly the same as at criticality if you're within the correlation length, and if you're far outside the correlation length, you should start to see exponential decay. Okay, so all this relation is saying is that basically it's just saying that most of the expected mass of the cluster comes from within the correlation length. So, and within there, the two-point function is roughly the same. Okay, so saying this, if you expanded this out as a sum over the 2-point function at PC minus epsilon, it would be basically the same as summing the critical 2-point function within a box of radius the correlation. Okay? So these other things have similar, some are more complicated than others, and they're all just heuristics really. But they're not so hard to see why they ought to be true. As I said, the scaling relations are supposed to hold in all dimensions. There's also some additional relationships called the hyperscaling relations. These are only expected to hold when the model is not mean field. So as I said before, we expect that there's this upper critical dimension. It's supposed to be 6 for percolation. Above the upper critical dimension, all these exponents should stabilize on their same values that they have for a Rashomon and walk, say. These kind of like Gaussian values, if you like. Whereas below the upper critical dimension, the lattice is not so spacious anymore, and the geometry of the lattice really affects the model in a non-trivial way, and it doesn't look like the high-dimensional model. Okay, and these hyperscaling relations are only supposed to hold in this low-dimensional case. Okay? And basically, the thing which is supposed to be differentiating the high-dimensional case and the low-dimensional case, leading to these hyperscaling inequalities and equalities, hyperscaling relations in low dimensions, is that when you're in low dimensions, what we believe is that there should basically be a bounded number of big clusters on any given scale. Okay, so there are various ways in which you could formalize this, but for example, you might say that if I take an annulus of size n, then there should only be one bounded number of clusters, distinct clusters that cross the annulus. Okay, so this would be a hyperscaling assumption. So this should happen in low dimensions, but not in high dimensions. So in fact, we know that in high dimensions, in the regimes where we can apply the lace expansion, we know that there are in fact many crossing clusters. Okay, and in fact, these hyperscaling relations are actually known to hold under an assumption like this in low dimensions, which I forgot to write the authors, but it's Chase, Kasten, and maybe someone else I've forgotten. Anyway, this is fairly recent stuff, relatively, and the two-dimensional case is completely proven by Kasten, and it's much older, from the 80s. But in general, we don't know that these things hold, so actually proving hyperscaling relations in low dimensions is open. Now, these conjecture relationships have been around for a very long time, basically as long as people have been studying these models, but it remains completely open to prove them in general. Of course, we know them in 2 dimensions, mostly due to this work of Kasten. We know them in high dimensions just because we know what all the exponents are. But in 3 dimensions, say, it's completely open. Now, what people have done a lot is to prove inequalities between the exponents, which are either just inequality versions of these relations, or they're slightly weaker and things like that. And there's quite a lot of work. So, and in fact, this argument that we wrote down earlier can be thought of as a very primitive kind of hyperscaling inequality. So one thing I should mention, by the way, that differentiates these 2 kinds of relations just at a completely formal level is that the scaling relations do not involve the dimension D, and the hyperscaling relations do involve D. So we had this argument where we just bounded this we bounded this sum of the 2. Yeah.
Is this a good time for a break soon?
Yeah, let me just finish this page and then we can take a break.
Yes, it's not right now.
So we saw earlier, this very primitive idea that we can always bound the sum of the two-point function by the expectation of the minimum, right? And this gave us this thing where if we assumed that we have some power law tail bound on the volume, then we get some bound two-point function, at least the average one. And you can think of this as giving you this primitive hyperscaling inequality here. Okay. So in order to prove the main theorem, we need to somehow strengthen this and come up with a more sophisticated thing to do instead of just this trivial bound here. And in fact, this is going to imply this stronger hyperscaling inequality. And this is nice because this is actually should be an equality in low dimensions. So we prove that the inequality version holds in all dimensions, but it should actually be an exact equality when the hyperscaling relations hold. So that's cool, and I guess I'll tell you about the proof of this after we have them. Right. I guess if anyone has any questions now.
I have a question about this hyperscaling inequality. So is this a new hyperscaling inequality that's not included in the ones that Chase and Tasaki proved in 1987 or so?
I believe so. I looked through all of these papers that I could, and I think it's new. This inequality is included in one of the Tasaki papers. And the one nice thing about this inequality is obviously that the proof doesn't use any properties of percolation at all. So this is just a completely general inequality that holds for every model. Whereas this inequality that I'll show you the proof of it is based on the BK inequality. So it's actually very specific to percolation. But yeah, I believe it's new. How long do you normally take a break for?
So 3 to 5 minutes.
Okay, maybe I'll go put the kettle on.
People to take a breath and stretch. And I should too.
Okay, so what I want to tell you about now is the proof of this hyperscaling inequality, and really I'll prove, of course, these inequalities only make sense if the exponents are well defined, but I'll prove an inequality that doesn't need anything to be well defined, which implies this if the exponents are well defined. And the idea is actually going to be to prove something much more general, which I think is really cool. It's like seems to be a fairly basic fact about percolation that just hadn't been noticed before. So I'll state this in a very general setting. We'll see there are other situations where you can get something out of this as well. So I'll just suppose I have an arbitrary weighted graph. So this function j is doing the same thing as before. So I have some graphs, some edges, this function giving them a weight, and then percolation is defined as before. So edge e, I have a parameter beta. I include the edge e with probability 1 minus e to the minus beta j of e. Okay. Now, my graph could be finite or infinite, I don't mind. And I'll take some set lambda, which is contained in the vertex set, and it's finite. And I'm going to consider this random variable. So I'll fix some value of beta and consider the random variable that I write like this, and it's just the biggest cluster, the size of the biggest cluster in lambda. So it's slightly abusive notation because there might be more than one biggest cluster, but the size of the biggest cluster always makes sense, even if this cluster itself is maybe over. Okay. So it's just the maximum intersection of a cluster in the percolation configuration with lambda. Okay, so I don't require the connections to be inside lambda. They can, I just take the whole cluster and the whole graph and I intersect it with lambda. Look at the biggest intersection that I can. Now, the theorem I'm going to state is going to tell us in extreme generality that it's very hard for this random variable to be much smaller or much larger than its median value. Now, to make the notation cleaner, instead of using the median, I'll use this thing that's like the median, but with 1 over e instead of a half. But you can think of this as the median. I'll call it the typical value. Right? So it's going to be the typical value of lambda of this random variable is defined to be the minimal value of n, so that the probability that this random variable is bigger than n is smaller than 1 over e. Okay. And so I've copied this theorem in. So what it says is that if I take any graph tool and any lambda, I have these universal inequalities, all the constants here, completely universal. It says that the probability that this maximum cluster is bigger than its typical value by some ratio alpha is always exponentially small in alpha, completely universal. Similarly, to be smaller than its typical value by a factor of epsilon is always at most linear in epsilon. Again, it's just completely universal. Okay. Moreover, if instead of looking at the biggest cluster, I take an arbitrary vertex, I fix some vertex u and I say, what's the probability this specific cluster has a big intersection with lambda, bigger than the typical value of the maximum cluster? It's bounded by this exponential factor in alpha multiplied by the probability that this specific cluster is bigger than the typical value. Okay. So again, this is saying completely universally, if you divide this random variable by its typical value, that is the family of all possible random variables you obtain that way is tight. And we'll deduce this statement from this more general one, and this statement here is just an analytic consequence of this one, which says that the probability that the maximum is at least 3 to the k times some number lambda, that could be anything, is bounded by the probability it's larger than lambda to this power 3 to the k minus 1 plus 1. And similarly, if I fix a specific vertex and ask for this intersection to be bigger than 3 to the k times lambda, again, lambda is just an arbitrary number here. This is bounded by this factor, one smaller, doesn't really matter, times the probability that the intersection is bigger than lambda. Okay, and you can see how this statement is going to imply this one by basically taking lambda to be this and a to be log base 3 of alpha for us. This you can get a lot of stuff out of this inequality. So one thing you can prove, which leads to other things, is suppose I have some graph. So you can imagine this is the long range model that I've been interested in the rest of the talk, or it's a D or whatever, or it's percolation on some finite graph. Maybe I might be interested in the case G is finite and lambda is the whole vertex set, for example. And suppose I know that I have a power law upper bound of this form. So probability that specific cluster is bigger than n is always bounded by some constant a times n to some negative. Okay. Then it follows from this inequality that if I take some set lambda, then the probability that this intersection is bigger than n, well, I get some theta dependent constant. I don't really care about that. So I basically get this from before, but then I also get this exponential term. So what this is saying is that, let's say, for example, I'm in the mean field setting, and I know that it's very hard. So I know that the probability of having sides at least n is like 1 over root n, okay? In the whole lattice, right? Then it's saying, well, if I'm interested in the probability that I have a big intersection with like a box, then of course when n is small and I'm in the middle of the box, I just get the same thing, right? I get this same thing as on ZD. But as soon as I start getting bigger than this typical value of the maximum, the probability becomes exponentially penalized. Of course, the proof of this fact from this inequality 2.7 here is just calculus. Okay. So let's see an application of this, which is this corollary here implies the hyperscaling inequality I looked at before. So again, we have some graph. Let's say it's the long range thing we're interested in, but it could be anything. And suppose I know that I have this power law upper bound on the volume tail. Okay. Then what I get is that the maximum, if for any lambda, the typical value of the maximum cluster is bounded by the volume of lambda to the power 1 over 1 plus theta. Okay, and then you also get some theta dependent constant, doesn't matter, and this constant a becomes an a to the 1 over 1 plus theta. Okay, and we also get this averaged 2-point function bound, where now the power of the thing here is the volume of the set to the minus 2 theta over 1 plus theta. Okay, and if you just plug this in and you remember what the definitions of the exponents are, this inequality here is implying the hyperscaling inequality that I wrote down before. But this is cool because it's actually sharp in many examples. So it's not sharp if you're in high dimensions and you take lambda to be a box, but it is sharp for high dimensional tori, for example, or say for the Oda-Shreni graph. And these bounds actually give you much simpler proofs of some classical things about these like finite percolation on finite graphs. So for example, the one basic fact about the Oda-Shreni graph, so that's just percolation on a complete graph, is that at criticality, the largest cluster is of size n to the 2/3, right? If you have complete graph of size n. Okay, so that's the theorem of Bolobash and Lukshak from the 80s. And it's not especially easy. There are various simpler proofs now, but at least for the upper bound, it just follows very easily from this theorem, because whenever we have a percolation on a finite graph and we have some infinite graph that like covers it, we can always have stochastic domination. So in particular, in this finite, the complete graph case, we can bound the cluster at the origin in the Oder-Shreni graph by a branching process, right? Gauss-Watson tree. Okay? And it's just a binomial Gauss-Watson tree, and it's very easy to prove that this Gauss-Watson tree satisfies, bound of this form where theta is a half, right? So you get the probability that the cluster of the origin in the Oder-Shreni graph being bigger than n is like a constant over, bigger than n, say, it's like a constant over root n. Okay? But then you apply this and you get that the maximum is bounded by n to the 2/3, right? Just immediately. I mean, you plug a half in as theta and you get 2/3 here. Okay? And similarly, if you want to understand percolation on the torus in high dimensions, we know that in high dimensions through the work of Orr and Slade that you have again the same 1 over root n bound on ZD. And by stochastic domination, it holds on the torus as well. And then you apply this and you get again that the maximum cluster size on the torus is bounded by the volume of the torus to the power 2/3, which again in high dimensions is the correct behavior. So I think this is a very cool thing. It's a very general thing, and yeah, it's just something that seemed to be missing. And the proof is not too hard. So let's first see how we deduce this corollary about the maximum from this theorem. So this is actually a very simple computation. So what we'll do, let's say m to be this typical size of the maximum cluster. And well, if we fix u in lambda and we sum over v of the 2-point function, this again is this same as the expectation at the intersection. This again we can always write like this. So by assumption, by using this bound here, right, we get this where we had this polynomial thing, and then we gained this exponential factor from the theorem. Okay, with the 1 over m in the exponent. Okay, and then you do a bit of calculus. It's just an easy computation. You get that this is bounded by a theta-dependent constant times m to the power 1 minus theta. It's basically because summing this polynomially decaying thing times an exponential thing is you should get the same as if it should be the same order as if you just sum the polynomially decaying thing up to the denominator in the exponential. On the other hand, we can also bound the same sum from below, or if we sum over both u and v, right, then this sum is the same as this expected number of pairs that are connected to each other. And that's at least, the number of pairs that are connected to each other is at least the square of the maximum cluster size. And, this maximum cluster size was at least m minus 1 with probability at least 1 over e. So you get that this is at least constant times m squared. And if you just compare these two, you sum this bound over u and then you compare them, you get the claim. Okay. So this is very simple. All right, so the last thing I need to tell you how to do is how to actually prove this universal tightness theorem. I'm going to prove it in this form. So I want to prove that having the maximum cluster, say, be 3 to the k times as large as lambda is at most the probability is at least lambda to the power 3 to the k minus 1. Now, this is going to actually be just a completely combinatorial argument, and then we'll apply the BK inequality right at the end. So remember what the BK inequality says, I have it written down here, right? It says that, so if you remember the notion of a disjoint occurrence of two events. So let's say I have two increasing events, A and B. Then I say that they occur disjointly and write sort of A circle B if I can find two disjoint sets of edges that are open in my graph, and they're both witnesses for A and B respectively. So I find, say, W1 is a witness for A, which means that just knowing that W1 is open is enough to know that A holds. And W2 is a witness for B, which means that just knowing W2 is open and just knowing that it's open means that B definitely holds. So the BK inequality says that, so A circle B is the disjoint occurrence. It means I can find disjoint witnesses for these two events. BK says that disjoint occurrence of two events has probability in most of the product. Okay. So the way this proof is going to work is I'm going to want to say that if this event holds, and I have that this, let's say look at this one, that the maximum cluster size has size at least 3 to the k times lambda, then I want to find 3 to the k minus 1 plus 1 disjoint witnesses for the event that it has size at least lambda. So this is going to be tons of these disjoint witnesses that all be disjoint sets of edges that each guarantee by themselves that the maximum cluster size is bigger than lambda. Okay? So this is going to be a completely combinatorial thing that I'm going to prove about just this inclusion of sets. So let's start with the following combinatorial ones. So I'm going to take an arbitrary connected graph, let's say locally finite. Actually, let's just say it's locally finite. And I'm going to take some finite set. So locally finite means all the degrees are finite. And I'm going to take some finite set of vertices A, which has size at least 3. Okay, then I claim I can find two disjoint sets of edges, E1 and E2, so that each of these sets, EI, spans a connected subgraph of G. And so the spans just means you take the graph that has vertex set, the vertices that touch V, touch EI, and you take EI as the edge set. Okay, so I want them each to span a connected subgraph of G. And I want that if I look at the set BEI, of vertices that touch an edge of EI, then it should have an intersection with A, which is between 1/3 the total size of A and 2/3 the total size of A for each of these two sets. So this is the first key combinatorial one. So let's see how we prove this. We're just going to construct this partition in kind of a greedy way. So first of all, it suffices to consider the case that G is a tree, because if this is true for a subgraph of G, then it's true for G as well. It's a subgraph, and I can always take a spanning tree. So let's assume G is a tree. And in this case, we'll actually take these two sets, E1 and E2, to be a partition of G. Let's call it T now because it's true. Okay. So, but remember, I need to make sure it's not just a partition, but it's a partition into two sets that span connected subgraphs of T. So I'm going to do this recursively. So I'm going to construct a sequence of sets of edges like E superscript I. So I'll start with, so my pen ran out of battery, so I won't be able to use the laser pointer anymore. Sorry about that. So I'll start with E0, will just be the empty set. And then I'm going to build up a growing sequence of sets. And I want to make sure at every stage that both EI and its complement span connected subgraphs of the tree. Okay. And what I'll also do is I'll define V superscript 0 to be the roots. Okay, so first of all, I'll root the T at an arbitrary element of A that I call rho. Okay, and then, so I think of it as kind of going up the page. Vertices have parents and children. Okay, and at each step I that's bigger than 1, I'll say VI, so EI and its complement are both connected, so I have a unique vertex that is incident, it touches an edge of EI and of the complement of EI. So how am I going to build the sequence? Well, if if this vertex vi, which is like the boundary vertex, if it has exactly one child, I'm just going to increase ei by this one edge going to this one child, right? And then vi plus 1 will be the one child. Okay. Otherwise, vi has at least 2 children. So what I do is I pick the child that has the fewest elements of A descended from it in total. So any one line up the tree from that vertex as a descendant, I want to pick the one with the fewest total descendants belonging to the set A. Then there could be a tie, I don't care, I just pick one of them. Okay, and that's how I construct this sequence. So, and once I've chosen this child with the fewest elements of A, I add all the edges that are in that subtree hanging off there. So the edge connecting vi to this child and all the edges in the tree hanging off of that child. Okay. So you can see inductively that I'm always going to keep this property at every stage that both ei and its complements are connected. I'm never going to break that doing either of these operations. And I was going to work through this example, but my pens are out of battery, so I can't do it. But you can see how this works yourself in this example. So, first of all, the root has 3 children, so I'm going to do the second step. And the child that has the fewest elements of A, well, I can pick either the middle one or the right one. Let's say I take the middle. It actually doesn't matter because so let's say I first take the middle one, then E1 would be the root and this one middle edge, right? Then at the next step, the boundary vertex is still the root, and now it has 2 children, and it's the one on the right that has the fewest elements of A. So the one circled with red is supposed to be the elements of A. So I take this whole tree on the right and add it to my set to get E2. Okay, so E2 would now be everything hanging off the tree apart from the bit that goes towards the leftmost child of the root. Okay, and then I'd only have one child left. Yeah, sorry, this thing about children, it should be children that are not already being taken up by EI. Sorry, this is always bad. But hopefully going through the example makes it clear. So I'm going to kind of, every time I take something, I'm going to throw that bit away. So finally, I only have this one child, so I'll just take that. So my edge set will just grow by this one edge. Then I'll have 2 children again. One has 0 elements of A descend from it, one has 2. So I throw away the one on the left. Then I finally go into this last bit and so on. So hopefully that was somewhat followable, even without the pen. Okay. So I just want to keep adding more and more stuff in this kind of greedy way, but always like the opposite of greedy, I suppose. I'm not sure what that is. I want to take as little from A as I can of each step while keeping things connected. So what you can see if you do this is that, so if you define Vi to be the set of vertices that touch EI, and V0 to be just the root, and then we look at this set of times in this algorithm where the set Vn, sorry, this should be the intersection of Vn with A, where the total number of points of A that I've got is strictly larger than A over the size of A over 3. Okay, so this certainly contains the termination point of this algorithm where I've got all of A because I have all of A, but it doesn't contain 0 because A has size at least 3. Right? So I can take the n to be the minimum of the set, and n will not be 0. And what you can see is for this value of n, well, I certainly get that the intersection of Vn with A is bigger than A over 3 because that's how it was defined. But also the previous step, the intersection was smaller than A over 3, and it can't increase by too much just because we're always increasing it by as little as possible basically at every step. So if you follow through the algebra, what you get is that at this time, at this first time where you switch to being larger than A over 3, you're between A over 3 and right, which is what we wanted. Now, if you just take this lemma about decomposing into 2 pieces and you apply it iteratively, you get this stronger version of the lemma, which says that if A has size at least 3 to the k, then you can find at least 3 to the k minus 1 plus 1 disjoint sets of edges, which is similar to before. So each of these sets EI is going to span a connected subgraph G, and the intersection of the associated vertex set with A will have size between total size of A over 3 to the k and the total size of A over 3 to the k minus 1. And how do you prove this? Starting with the other lemma, you just iteratively apply the lemma to these pieces, and you stop when it, in this kind of branching fashion, and you stop whenever a piece is smaller than this upper bound, right? And if it's bigger than the upper bound, you can apply the lemma again, and you won't get anything too small, right? So you just keep applying until you've broken everything up into pieces that are bigger than this, are smaller than this, and they must be bigger than this because they can't drop by too much. So once we have this lemma, as I said, this universal tightness theorem really does just follow immediately from the BK inequality, right? Because it says, suppose that this event holds, that I have a cluster that has a big intersection with this set lambda, right? Bigger than 3 to the k times lambda. Then I can apply this, and I get these 3 to the k minus 1 plus 1 disjoint sets of edges. I applied this with A equal to, with the graph being equal to the biggest cluster, and the set A being equal to the intersection of that cluster with the set lambda. And I find all these different edge sets that are disjoint, and they each connect to a large number of things, right? So I get this inclusion of sets. I apply the BK inequality. Okay, so I guess I'll stop there. Yeah, thanks again for inviting me. I'm happy to take any questions.
Okay, thank you. So we will unmute everyone to thank Tom. And you can unmute yourself now if you have questions. I'll stop the recording.